Welcome to another episode of Robo Papers. Today, we're super happy to have Tom Zhang, the founder and CEO of Daxo Robotics, joining us today. Today is a little bit different. It's not like a deep dive into a specific paper, but it is a deep dive into what me and Chris think is a very, very interesting project involving a very unique take on robotic hands. Tom, thanks for making the time. Maybe, as a start, you can share a little bit about yourself first.
Sure, yeah. I'm Tom Zhang. I graduated my PhD from Penn Grasp Lab last year in December. So I've been running my startup full-time really for 9 months. And previously, as I started my company in my third year as a PhD, we were actually doing agricultural stuff. Right? We built devices to make apple picking faster. But then, to help with apple picking, because the apples are very fragile, I invented this soft robot for apple picking. But the business case didn't work out. It was, it's a very seasonal, and you only get about 3 months to iterate every single year and 3 months of apple harvesting. But then you only get to work on it for maybe 2 weeks because the growers are always so busy. They don't want to work with you sometimes. So the business case didn't work out. We pivoted to a small device and we had some success there. We sold 600 units to make apple picking faster. I'm not going to go into details. It's for apple stem clipping. But then that soft robot was so amazing when I built it. Actually, I have a video here. This is the soft robot that I invented for apple picking. It was supposed to be a replacement for the existing robotic arms. As you can see, I'm doing some teleoperation here. It can go up, down, left, right, in and out. And the idea is that because this is so soft, it should not bruise any apple when it's picking the apple. So there's supposed to be a suction cup in the front. And then, there's a camera here. It sees where the apple is. It go grab the apple, right? So this is like the soft robot that I invented. We didn't build this further for apple picking, but it became part of my PhD. Okay. So I studied this soft robot mechanism for the past 2.5 years. By the time I graduated, I was like, wow, it's so compelling. And everybody's building robot hand for dexterity, but it seems like they're just not that dexterous. They're all rigid, they're plastic shells. It seems like that's how people have been designing mechanical, mechanisms or devices for the past 2-3 decades, and it's still like the same thing. They're not dexterous. But I look at the soft robot we've been studying, we think this is gonna be a complete paradigm shift. So we pivoted fully in late March to focus on building a robot hand using soft robot mechanisms. And in 3 months, early July, we launched this robot hand video that went kind of viral on X. I will play the video while I talk about what this is, right? So in this video here is hand tracking, and there's no electronics in the hand at all. That's why you can hammer it. It won't break it. And it has different modes of grip. That's a tripod grip right there, a pinch grip, and all these grip, right? So these are not automated. These are with hand tracking. So I have my hand on its side, and using a RealSense camera, it's tracking exactly how my hand is doing it. With a very simple algorithm, we're using media pipe library to track my hand position. And the cool thing is it has infinite degrees of freedom, theoretically. As you can see, every single joint can move. And this spooks a lot of people, right?
So that's hand tracking. How are you making your hand go, sorry, all the way back?
That was not hand tracking. So give me 1 sec. This right here, this is not hand tracking.
I was thinking which undergrad did you torture to do this? But you put me off sec. I was like, what?
Yeah, okay, so I wish my hand could be this dexterous, but how we did this was actually, the hand tracking was a very, very primitive, right? I did not even map every single joint. I just did a very simple retargeting. But here, what we did was that we released the control for every single joint to a joystick. Okay. So in here, there are 3 different segments that we have some tendons that's attached to it. And we use a joystick to control those stages. And this is the kind of behavior that we can create, right? So we always say that the hand that we build is a superset of all hands. And this is what I mean. If we want to retarget to a human hand, that's no problem. But if we want to go crazy, we have all these extra capacity that we can explore like this. Okay. Yeah. And then, so this is a demonstration of the payload. For the first version, we did not deploy all the motors yet, but we already achieved a 7 kilogram or 70 Newton payload with a hand. In the most recent release, we can already pull 5 kilogram per finger. Okay. And the stiffness can change. That's stiff. And now it's soft. And this is what's very intriguing to a lot of, I guess, machine learning scientists. If you look at when I move the finger around, we have very rich sensing coming out of the hand. And it has 108 motors, so 108 sensor. And the left hand is also the right hand, so it's one SKU. And this is to show off some of our simulation capabilities. We build our own simulation asset. And the next frame, we think this is super cool. This is dynamic pen spinning using 2 fingers. And so what I want to say
And
here,
this is 0 shot sound real, or is this?
this is actually teleoperated.
Okay,
Yeah.
sorry.
So we did not automate this yet. But the cool thing is this, right? The day we build out our second finger, we can do a pen spinning using just teleoperation, right? So, and I'll show you the video. So this is the day we built out our second finger. It can do pen spinning much more dynamically than what I showed in the previous video, even. Right. So, but then, you know, we did a lot more work afterwards. We did a circle drawing that is using a neural network. And we also did a scissors cutting papers. And also most recently, we used our hand to swipe the phone and make a phone call to my cell. So all of that, right? So this is the hand that we have built. I know that we're probably still in the phase of a self-introduction, and some of our video went viral, and people really think that our approach is very unique. They're intrigued. So I've been engaging a lot of these conversations, and I'm learning a lot through the process too, trying to think about how do we improve the hand, how do we make it different. And, you know, if you ask me what are the 2 defining features that makes our hand very different, first of all, it has infinite degrees of freedom, theoretically. And the way you count your degrees of freedom, I mean, that's another conversation. And the second defining feature is really the high redundancy and the complexity in this hand, right? So the crazy thing is we have 108 motors. We may be dialing it up, by the way. If we compare this to some of the other robot hand, like, so the Tesla Optimus version 3, I believe it has 22 motors, and the clone robotics hand has 27. And some of the lower degrees of freedom hand, like the Inspire hand, some version have 6, right? And we just have a lot more. And that brings many, many advantages. And people also have expressed concerns about some of the disadvantages and weaknesses. And I guess like that, those are some of the things we can discuss further as we continue the conversation.
Okay. Well, as you talk, I've got so many questions, but this is super awesome.
Yeah.
I guess maybe before we talk about the hand, I do want to dive a little bit about your earlier work.
Sure.
So, you know, that setup that you have there where it's like 4 different stick that is basically doing things. And I guess you consider it, and you were saying this is so-called soft robotics. Like, could you broadly say a little bit about what to you is soft robotics? Is it because of the mechanical setup that it just makes this kind of setup a lot more safer or compliant? Like, what do you think is a trade-off? Like, you know, obviously most people are doing, I guess, the reverse hard robotics, if there's such a term. Yeah, what is the trade-off here? Because clearly what you're doing is very, very unique.
Yeah. It's I think this is a spectrum, really. And, you know, correct me if I'm wrong, Chris. You know, when we are talking about like rigid dynamics, say when you have a robotic arm, right? You can model that robotic arm as 6th off. I mean, so like the position and the orientation. But really, if you think about it, even a rigid link on a robotic arm can flex. Maybe not as much, right? But here, I'm using these 4 things that you can visually tell that it's flexing, and you need a lot more parameters like to define it. And it's a spectrum. If you go to McMaster, you try to buy, say, like a polyurethane from really soft to really hard, and it's a complete spectrum, right? And so I don't think it's a clear line. And as a matter of fact, I don't like to call our robot soft robot. I just like to call it like robotics. But then this is, so going back to academia, the way people study it, right? I mean, so what I show here, this is called a parallel continuum robot, and it's usually published in the soft robot community. And our robotic hand, that's actually called a tendon-driven continuum robot. That's also published mostly in the soft robot community, right? And so it's really a spectrum, but it really depends on just like where the community is and where the audience is. But I see everything just as, you know, whatever you need, man. Like if you want more softness, if you want more rigidness, you can add it in there for your purpose. Yeah.
Got it. Would you say like, I'm just eyeballing this, right?
Yeah.
Is this setup, do you think, gonna have the same kind of precision as what you get from more of this, like, you know, industrial grade arm that people use? Like, yeah. Could you comment a little bit?
So we're talking about like the precision, right?
Yep.
And in fact, that's one of the things that we addressed with our robot hand. I'm gonna pull out this video. and
Mm-hmm.
talk about the precision in our hand. First of all, I mean, you can take a look at the video of our robot using a hand phone right there. So the swiping, right, and finding that phone book and clicking on it and scrolling down and finding my number. So that precision is probably about millimeter. Okay. And if I go to the circle drawing that we show, this is also the first ever circle drawing by a robotic hand without any wrists or arms. Okay. And we're holding the notebook ourselves. But if you look at the consistency of the circle drawing, that's about maybe 1 or 2 millimeters, right? But then if we fix like the notebook, it should be about millimeter, right? And so now the way, say, it's a trade-off, when you have very few tendons, that's how a lot of these like tendon-driven robotic hands are. And also for soft robotics, the precision is a huge problem. But here we have about 20 tendons per finger. And so in total, when we're drawing the circle, we have 40 tendons. The precision just improves. We did this experiment. We did not really
So this is also why you were saying there were advantages to having 100 motors in the arm. Okay.
Exactly. So one interesting experiment that we did was, okay, we have one finger, we have 4 tendon versus 6 tendon, 8 tendon, all the way to 20. And we do an open loop control. Basically, we let the finger draw a circle in the air, and we look at how much noise is in that trajectory. It becomes less and less, right? It actually plateaus. Say from 4 to 8 to 12, then it's going to go up like linearly. And then say from 12 to 16 to 20, then it's going to plateau a little bit. Right.
Why is that? Is it like all of these are kind of the error is canceling each other out, or what's going on? Why is that? Why does this happen?
Honestly, I don't have an answer because we're the first guys who actually built this. So
what made you think it would work, I guess? Why'd you build it?
Yes. I used this very loose analogy of weak learners, a group of weak learners make a strong learner, right? But I don't think it's the right analogy, but that's what was in my mind when I built this thing.
And so from this, it looks like pretty good repeatability too, which was actually the next thing I was going to ask about. Like, it really is just, okay.
Yeah. So on the repeatability, there's some like a very interesting finding about this hand. Do you know reservoir computer?
No.
So
What's that?
So like reservoir computer is this idea in scientific computing. What it is you don't train a neural network, you don't train the entire neural network, but you have this blob of reservoir, randomly connected neurons, and then randomly initialized weights, right? You use it as a way to project low dimensional signal to high dimension, and then you only train a small readout neural network, okay? So this reservoir is like so random, but like what you do is that every time you have to have an alignment period. So when you are training it, you have to run the reservoir for a little bit, and then it starts to stabilize, and then you can use it for regression tasks or prediction tasks. And our hand has a very similar property in that when we're drawing the circle, we need actually a period of time to align it. Like when we start drawing, maybe it's drifting towards like somewhere. That's like the transient part. Say it draws a few circles. Now it starts to converge and becomes highly repeatable. It's another interesting analogy. I just have a lot of analogy because my research was really scattered all over the place. And it all converged like to robotics, but I use all these weird analogies everywhere.
So I see. Interesting. So what you're saying is that it could be like, let's say coming back to this specific example of drawing circles, the first 1-2 circles may not be super precise, but by the third or fourth, it's basically hitting the spot.
Yeah, exactly. And the other interesting thing is this, right? We did not even know if the hand can draw a circle. We just didn't. So we can teleop it, and we can see that, wow, it's drawing all these like noisy trajectory in that space. It should have that capability, but we did not have the conviction, right? So what we did was that we have this like simulation asset. We use reinforcement learning. We train like a base policy. We put it onto the hand. The circle that it draws is actually not a great circle. It's more like a droplet, even with some like sharpness in the trajectory. And then we just manually fine tune it. It was like, is it even possible? As we fine tune it, it became more and more circular. Then we're like, wow, we can draw a circle. It's almost like we built this gold mine of different physical skills that we didn't even realize existed.
Interesting. Can I ask, like, for other, I guess, hands that are also tendon-based, it sounded like so what you're saying just now is that you guys were the first one to push it to this so-called limit, like maybe 20 tendons. The typical, like, how many would you find typically in a single finger?
Right. So it varies from hands to hand. Usually what they do is, say, for each of the finger, some of them use passive mechanisms. they will use one tendon to control the top 2 stages, and then they want maybe two degrees of freedom here. They use 2 tendons. So sometimes it's about 3 tendons per hand, right? And that just brings a lot of problems. Like the most obvious problem would be the payload. It just doesn't have the grip strength required to do any useful tasks. And the other thing is the wear and tear. It's like, because now you're offloading most of the task to these 3 tendons, and the 3 tendons are even serving different purposes. So if one tendon snaps, that's a single point of failure. You lose the capability in that entire finger. And also there's this huge debate in tendon-driven hands about the wear and tear. So some people say, hey, you can use like thinner cables, and that would not have much friction with these like sliding surfaces. But the thing is, the payload becomes a problem. And now if you use a thicker braided tendon, sure, you have more payload, but now it's going to be a lot more friction between the tendon and the sliding surface. It's more wear and tear, right? And what we realize is, okay, what if we just use a lot of the thinner tendons? And then we get the best from both worlds. We don't have the problem with wear and tear, and we don't have a problem with payload. And sure, if you're not happy with our existing payload, we just throw more motors. It's a very easy thing for us.
It sounded like, because I was thinking, the more tendons you have, the more, I guess, motors you have, the more complex it will be to assemble and manufacture a single finger. Would you say that's the case, or? Yeah. But it sounded like it's fairly straightforward for you guys to even add a few more.
Yeah. So that's actually a very intriguing question. So I'm gonna come back to the fundamental philosophical shift here for a little bit. Okay. I think what we're trying to do here is we're trying to build complexity into robotics. And I talk about this in some of the previous podcasts, but I really want people to understand the difference between a complicated system and a complex system. Okay. A complicated system is where, say, you have a car, an airplane, you have thousands, millions of different parts serving different purposes. Now, that's complicated. While a complex system is where you have the same unit, but you repeat it over and over again. All of a sudden, the collective behavior, the overall emergence of its, a performance is better. Okay. So here, every single finger is the same. Every motor module is the same. You just repeat it over and over again. So this is a complex system. And now what you were talking about, and your question, Mike, is about the cost of complexity, right? So complexity is great. In natural phenomena, I mean, like human, we're also complex systems with the result of emergence from our DNA, and a flock of birds, that's also emergence, so, but like, what's the cost of that? So assembly, the challenge in assembly is part of the cost. Also, the cost of our BOM, like the whole device, how expensive it is it to include 100 motors in the system? That cost is also the cost of complexity. And also like the serviceability of our system. Like, what if in the future, say, some of the tendons break in there, how easy it is to fix them? That's also the cost, right? I will try to address each one of them. First of all, in terms of the BOM cost, this is another surprising thing. You want to guess, like, what's the cost to build this hand?
Wow. Okay.
We have 108 motors.
I have a guess.
I don't know, a hand like this with so many degrees of freedom. But but the way you're setting up is like, it gotta be a lot lower than what I initially thought. I don't know. I mean, it's
right.
Yeah. So
is it 1,000? I don't know. Is that?
It's $1,200.
Okay.
Yeah.
Okay. Cool.
So the BOM cost is $1,200. Right. And this is go ahead.
This is how many degrees of freedom again?
This is 108.
Gosh.
Yeah.
108
108 active degrees of freedom or actuated degrees of freedom, and the infinite passive degrees of freedom.
Got it.
Right. And so when you use
I was going to ask about this BOM cost thing, actually. Sorry. But this is like, so the continuum actuators, I guess, are presumably just substantially cheaper than like a traditional like harmonic drive or whatever you put on a robot. Is that?
Yeah. So
okay, by many orders of magnitude, it sounds like. Is that like, why is
each
that?
motor is only $5?
Cool. Okay.
So
nice.
we're using a simple brushed DC motor that's off the shelf, and each one is only $5. Simple spur gear, because when we're building this thing out, right, one thing we're thinking about, okay, we're using a completely different principle, and we believe that using more superior principle, even when you use very scrappy parts, the performance should be 10x. That's why we just grab whatever the cheapest motor we're familiar with, that's cheap, we bought it, put them all together, and the result is this. But our next version, we're actually gonna buy slightly more expensive motors, and you will see a jump in the performance. So after building this thing, we're very confident in, the level of performance and tasks that we can show. It's going to be super exciting.
How big is the drive unit on this then? If you've got 108 just like off the shelf DC motors, is this just like the size of a suitcase? Is that?
Yeah.
I assume it'll be. Yeah.
Yeah.
Okay.
It's about the size of a suitcase, right? So.
Yeah.
And when people visit our office, when they see the robot, they get very surprised.
Yeah.
And we get this question a lot, like, can you shrink the form factor or something like that? So like, first of all, I think robot hands, if it's truly capable, it should be enough to do a lot of work at a stationary workbench. Is miniaturization of our motor array even necessary? That's my first question. But now, if we're pushed to do so, that's also fine. Because for the first version, we did not optimize for the motor space. For the next version, we're going to have a 98% reduction in the volume with almost no degradation in the performance. And we should have it ready around the end of the year or early next year. And it will be able to integrate into any existing robotic arm with payload about 7 to 20 kilograms. Yeah.
What's the current payload on this one?
No, so I'm talking about the payload of a robotic arm.
Oh, sorry. Okay, yeah.
Yeah,
sure.
Yeah.
Okay.
Yeah.
Yeah.
So the whole thing will be self-contained. Instead of having a big base and now you got to put the hand somewhere, you got to route the tendons and stuff like that. So the next version will be integratable to a robotic arm.
Actually, I mean, sorry, you mentioned two other like aspect of complexity, right? The cost of complexity. Cost, and then the other one is manufacturability, right? Or assembly.
Yeah. So we addressed the BOM. Now, in terms of the manufacturability, so like for DFM, right? And interestingly, our team is all very full stack. I had manufacturing experience, so I had experience. So, and by the way, I'm a computer science PhD, but I did all the injection molding, sheet metal, fabrication, elastomer, like casting and stuff like that. So one thing we do is that when we're designing this finger, we work with a supplier directly. So like when I design my finger, I go directly to a supplier and ask them, can you produce this at scale? Right? I would not be very concerned if they say, oh, this is not a problem. So for example, now I will address the assembly problem. The finger itself is fine. The finger without the tendon can come out of one cast. Okay. You have a flexible center bone and with some hard plastics as the ribs. Now, what's going to be challenging, and the motors, of course, they're off the shelf. That's all very standard. But what will be challenging is to put the tendon through each of the ribs. And I did everything by hand so far. Okay. And it's a pain in the ass. But yeah, go ahead.
It's like threading needle, like threading like 20 like tiny strings through very tiny holes. Is that what I'm imagining? Is that something like that?
Exactly. And the thing is, when you were threading the tendon through the ribs, when the tip of the tendon gets frayed, now you're screwed. And then threading that one tendon is going to take a long time. But then, we had all sorts of like tricks. We dip it a little bit of like plastic on it to make it a little harder, so it's easy to thread. So we optimize the process a lot through the assembly process. I mean, we're doing all the assembly so we can learn about the process ourselves, right? But then we also talked to some manufacturer. They said in the fabric industry, there's this like sewing machine, like with a needle that can just punch through the fabric, And so we can customize those machines to mass produce our finger, no problem. But the thing is, in the short term, we're not going to do that because that's a lot of high capex, right? And the other thing is this, I think because we have the recipe to make our hand just better and better, I think our hand will be the first hand ever, or at least someone else, and if they follow like the same approach, will be the first one to self-assembly. We can actually do the threading of the tendons through each of the ribs ourselves. Because, I can see the precision and the payload and all the dexterity getting better and better with our approach. And I think it's going to be very achievable. I mean, at least compared to any other rigid robot hands. Yeah. So incredible. In terms of like assembly, so I guess like that's the cost of complexity, right? And one last thing is about like the serviceability. So say you have a bunch of tendons, you have a bunch of motors, and what if they break? A lot of people would say, okay, wow, so you have so many motors, so many points of failure, that's going to be very problematic. But there are a few things I actually want to say here. First of all, like when we have so many motors, because the load is fully distributed, and so far we have not overheated or burned any single motor. And the other thing is, so in our experiments, if you kill 10%, 15% of the motor, the hand can still operate because of the high redundancy. We don't have a problem with that either, right? So we think about, okay, serviceability. When we sell our systems, say, to a factory, there are two kinds of maintenance, reactive maintenance and preventative maintenance. People only want to do preventative maintenance, right? So they send some guys in, say, like every 3 months to fix it up, and then, everything will be operating like no problem. But what they don't want to be handling is, okay, something break unexpectedly. Now you got to send a crew in. That's very expensive. So with our stuff, the hope is now it's so robust, you don't have to send some guys in for that reactive maintenance. All you have to do, go in every 3 months, swap out like all the bad motors, right? And also like, so there's a lot of engineering solutions to address that problem. Like we're designing each of the motor module to be very modular. It's like you snap it out. You snap in, you snap out. And right now, the hand, the motor, and the tendon, they're integrated. For the next version, the hand will be separable from the tendon, and the tendon will be separable from the motor. And there's a lot of
each finger going to be separable too? So you can like pop off a finger if the one gets like cut or something like that?
Yeah.
Damaged?
Exactly.
Yeah, okay.
So the finger will also be replaceable. And also, so the other thing that I forgot to mention is every single finger is the same. Yeah. And for the pinky, you just have to cut a middle finger shorter. Yeah. And now
why even have a pinky? Why not just 5 equally like sausagey fingers? What's the
That's another great question. And I will pull out my video to tell you why we did that. Give me one sec. How do I we didn't even want to build a 5-finger hand in the very beginning. We built a 3-finger hand like this. Okay. Because with 3-finger, you can do in-hand manipulation. So I think having 3-finger is quite important compared to having, say, 2, which you can't really do in-hand manipulation. But the problem is, and this tweet, we got 500,000 views, and we got 200 comments. But this is probably one of the greatest robotic meme thread ever produced because people think it's a sex toy, okay? It's just like, it was quite a scene and everybody was retweeting it. It was like spread among all the meme groups, but people just don't take it seriously. So then we were like, okay, maybe we should just build a 5-finger hand like a human hand because that will prove that we're actually better.
Okay, so it was just to make people, all right. I mean, that's a good answer.
Yeah. Yeah, it's
so 3
incredible.
Fingers, perfectly capable. People don't take you seriously. 5 fingers, no one thinks it's a sex toy.
Yeah,
right.
Yeah,
so
exactly. But like at the same time, it's also like it's like good and bad, right? You know, our 5-finger hand, we demonstrate a lot of the capabilities, and people really like it. But now people think that we're a robot hand company. I mean, like we are a robot hand company, but really, I think what we can monopolize right now is high-dimensional control. Controlling 108 motors all together to generate these behaviors that are coherent, that seems useful. I think that's what we have been working on for the past 3 months. And if nobody has this like system, they don't even get anything to work on this high dimensional control.
Yeah, in fact, in my mind, when you're talking through all this, like it doesn't need to be just in the form factor of a hand. It could be the entire torso, maybe. I mean, this could, if you make it, let's say 5x bigger, is literally someone's arm, you know, maybe it's an octopus arm.
Yeah.
Would you say, I mean, that it all translate, right? I mean, that whole philosophy.
Yeah. For manipulation, we're building this, so every finger is the same. We're still building a finger, you know, we're not building like any other things because looking across all biological systems, a cylindrical structure is almost the fundamental building block for any manipulator. Elephant trunk, octopus tentacle, the tail of a monkey, the cilia in our windpipe, they're all cylindrical structure, right? That's why we picked this. But then if we go one layer below, it's really, so when I talk about high dimensional control and also embracing complexity, I think about why can't we address some of these long tail problems? I will name one example, say manufacturing of wire harnesses. Just wrapping the tape around a bundle of wires, this is not automated. For the low voltage wire harnesses, this is all done by hand. There are machines say, okay, it's a 1 degree of freedom, just a motor that's rotating. And, you know, it's like rotating a roll of tape around a bundle of wires. They're doing that. But the thing is, it doesn't satisfy the requirement. So the coverage ratio between each segment of the tape and also how tight it is, it's just not good enough. So we handle like 90%, like the bulk of the task. But there's some like a long tail problem, even in that one particular task that's not addressed. Now, what we're saying here is, okay, you need more dimensionality. You need more complexity. Say you have that 1 degree of freedom thing. I can just add a little bit of gadgets on there with, say, 50 tendons coming out. And you can reinforcement learn it because it's a very tractable problem. And you can just improve the performance in the last bit of that task. That's the fundamental thing that we're really thinking of. So the hand is only one embodiment, but we're eyeing all these long tail problems across industries. Yeah. I don't know if that makes sense. What do you think, Chris?
No, I think that makes sense. Yeah. I was thinking it's interesting that you're like I was thinking about the fact like the fact that you're a CS PhD getting into the mechanical engineering thing. It seems like everybody is very unhappy with their current like dexterous manipulator capabilities, and so you have all these AI people like yourself starting to build hardware because our hardware isn't good enough. And as is like, and to be able to solve all these problems, it seems like we need new hardware like this. So that was it's an interesting trend. That's been I really like this.
Absolutely. Like, I feel like if you're serious about your software, you should build your own hardware. I mean, like quoting Alan Kay, right?
Right. Yeah.
You had a question, Mike?
Tom, good. Yeah, I do. You know, just now you were showing this diagram. I mean, this video where you almost have like different dots. It's almost like a touch sensing, like hotspots thing. Could you talk about the touch? How do you get it out of the box?
Yeah.
Like, where is the sensing coming from?
Okay, I'll see. This that's another thing we're highly proud of. I'll show you. I've got too much trees going on here. But okay, so this video right here, right? So every single actuator that in our hand has a force sensor. So we have 108 force feedback throughout the system. And for our next version, we're adding encoders as well. And
this is just like from current draw from your cheap off-the-shelf motors, right? Is that the force, or are you doing something else too?
No, what you're seeing here, this is not the current draw. This is actually tension in every single tendon.
Oh, okay. Yeah.
We have basically an inline sensor in every tendon. Yeah. So, and now all the motion in the hand is actually force control. So we're sending directly to every single tendon how much force we want to pull in that tendon. That's how we generate all the motion. Maybe that's a little surprising too. Yeah. Now, this sensing modality, what it gives us is the information of contact. Okay. One small experiment that we did was if you stick up one finger, you tap on it at different locations, you record the data of the location you tapped and the force signature from all the sensors. You can train a decoder to tell you in the future where you tap on that finger. So this is it's not the same as tactile sensing, you know, but the thing is a lot of the demos from tactile sensors are doing that. Right. So they're like, okay, I tap on here, I can tell that I tapped and stuff like that. We don't even need tactile sensors to achieve that. And why do we need encoders in the future? Because force sensors tell us about the contact information, but encoders will tell us shape information, right? Based on how much every single tendon has extended or contracted. Now, with both information, you basically have a very rich sensing for dexterous manipulation tasks. Right. And we're super excited to see like what we can get like out of this data. And it's so high dimensional, right? You can't really just like use the data, post estimation, like 3 numbers for the position. You have to train a decoder for it. Yeah.
So I guess like, let's say the case of like the 2 fingers flipping, the pen.
Yeah.
What you're saying is that, but you take the signature of across all of these 108 and you can basically now pretty much know where is it touching and as the pen is spinning.
Exactly.
Incredible.
Exactly. Yeah. And also at a high
this
frequency.
encoder could be very cheap. Yeah, exactly.
Yeah, these encoders are like
frequency.
So the encoders, so for the force sensor that we use, just a few cents each. Yeah.
Wow. Is that partly because it's just measuring tension, right? Is that the idea?
Yeah.
Okay, cool. That's really neat.
Yeah. And then so say when we have, and of course, like I also think that vision is very important. And especially that cameras are so cheap, right? So we're going to have that in our next system as well. So, I mean, people always like debate about how important tactile sensing is, different like sensing modality. I think in dexterous manipulation, people don't have a good idea on what sensing modalities are important, especially for robot hand, because there's no useful tasks performed by robot hands yet. With a parallel jaw gripper, there's more consensus. It's like a wrist camera is very important, right? But for a pair of robotic hand, people don't have any idea. People are building these like tactile sensors because they think it's important. And, as a human, we are aware of our tactile sensing and our vision and all of these. But for the force sensing that we're doing here, and also the encoder we're going to add for every single tendon or muscle, we actually think this may be more important because it's more similar to our subconscious sensing in our muscle fibers. And so we're not building reasoning right now, right? We're not training like VLAs. We're more training like the cerebellum. So for each individual skill, right? Using reinforcement learning and stuff like that. So it's muscle memory and it's subconscious. We actually think these subconscious sensing modalities will be more important than some of the stuff that we're aware of. It's a huge hypothesis. It goes against any of my PhD training to be rigorous, but we'll find out by building out our next version.
Exciting. Yeah. It feels very scalable, which is exciting. I feel like current robot hands don't often feel very scalable, I would say.
Yeah. And they're very expensive.
I mean that, there are a few aspects of it that I think
exactly.
really unique, and I mean this is definitely a very unique design, but also I feel that it is a much closer like similarity to actually how like biology has evolved. I look at a lot of these like I guess robotic systems now, like usually they put, for example, actuators at the joints. But I look at myself, our actuators is in the core, right? Ultimately the joints are all just tendons and cables running through.
Yeah.
And the issue with putting actuators here is that the angular velocity ends up being, like the momentum ends up being huge, and that's why it's literally not that safe. Whereas something like this it's just inherently very compliant. So like, all the things that you were doing to it, you flick it, it's no problem, and yet it has exactly what you're doing here.
Yeah.
But while at the same time, it has tremendous load, because if you really squeeze it, it can lift up like, 10 kg or something like that.
Yeah. Yeah. You actually touched on a very, very important point, Mike. Talking about having a joint being a motor versus using tendon-driven mechanisms. And also like Chris, like you definitely know this. There's a video from Agility Robotics very recently about someone pressing down on the hand of digit. When they release it, it goes up crazy, right? When you have a motor at the joint, there's just no solution for how you can hold your arms still when you let go of some load, unless your control frequency is crazy high.
Yeah, exactly. You need 1000 hertz. You need 1000 hertz, and you need an encoder that is super well calibrated, and they will never go out of calibration.
Yeah, exactly. Yeah. But then when you have like a tendon-driven hand, especially for the kind of hand that we build, we have tendons on both sides. We can do co-contraction. What that means is you can stiffen up your arm by having motors on both sides contract, right? When that happens, and you can experiment with your arm, by the way. I do invite people to like do the experiments like themselves. Try to push on your own arm. It will come up. But then if you stiffen up your arm by just like contracting your muscles on both sides, all of a sudden you don't go up anymore. So there is a solution when you have a co-contraction compared to, say, when you have motor there. Yeah. And also like the other thing is like the pen spinning demo, right? We did our teleoperation. It's not even like automated, but we're still very proud of it. Because like even with teleoperation, I don't think any other rigid robot hand can do it. And so one of the hypotheses, and also like talking about the compliance and the analogy with biological systems, is that so when we grab a pen, put it in between the fingers, it's already a steady state. It's already stable, right? It's almost a better warm start for tasks than, say, if you put a pen in two rigid surfaces and then you can't even stabilize it. It just makes like a lot of the learning problems and the algorithms easier to write.
Yeah, that makes all the sense.
Actually, I'm curious, like Tom. Sorry, Chris.
Go ahead. Mine's a little bit of a tangent, so yeah, go ahead.
Yeah, well, actually, mine is kind of a tangent as well. But I mean, I was thinking, like, why do you think it took? Because these things, like you're talking about chip motors, these tendons, like chip sensors, motors, these have been around for ages. Why do you think now someone like you come along that is able to do it now? Is there something about the timeline, or we're just stuck in a local minima for years? No one want to explore this. Like it seems to me the hardware is there. Like the basic hardware is actually been there for years.
Yeah. I would say, when I was selling my product for apple orchards, people asked me the same question, like, why have nobody ever thought about this before? And I guess I get asked about my hand as well. But if I'm really to pinpoint right now, first of all, the huge development of humanoid robotics around the world, especially in China, is driving the cost of these motors down crazy, right? Here we're using brushed DC motor. But then if you look at some of the coreless motors, which are some of the hardest to make motors, right? Even for those motors, their costs are going down. So we can afford to use a lot more motors. And the other thing is like, I think people were building like robot. They think AI can do a lot for robotics. See, when AI first started, like with all the computer vision and stuff, people think about robotics, right? They put all of these on existing platforms. They realize, oh, wow, it's not enough. And here we talk about the cost of complexity. But now the cost of miniaturizing a motor, put that in the joint of a finger, is a lot more than the cost of complexity. And when that balance is broken, there will be some guy like me that show up. right? Because like, so for robotic hands, there are 3 approaches. A direct drive, you put a motor in the joint, and the other one is called like a bar linkage. So you have your motors in the palm that links your finger. And the third type is a tendon driven. So for both the first and second type, the problem is that the cost of miniaturizing that motor into the hand with the required power density, precision, and durability is outweighing the complexity's cost. And I think this is like the tipping point, right? And I'm pretty convinced that for the next 20, 30 years, we're going to see more and more mechanisms, companies, robotics, even machines built off this line of philosophy.
And the line of philosophy, just to reiterate, is a lot more simple components, the same components, but you combine them, I guess, the way you do it, and then the whole system has very unique, complex properties that just emerge.
Yeah,
right.
Yeah, exactly. Yeah, and also, by the way, my first paper was on swarm. My research was actually at the intersection of dynamical systems, machine learning, and robotics. My first paper is learning to swarm. How do you learn a decentralized controller to mimic the flocking behavior for swarm birds or school of fish? Huge inspiration for me.
Interesting how the dots connect.
Yeah.
Sorry, Chris, you wanted to ask a question.
Oh, well, I guess it also strikes me, and this is kind of like AI first hardware, right? Like you couldn't write a model predictive control routine for this, most likely, right? So like that's another reason why people wouldn't have done this even like 2 years ago, I would guess. So like just kid couldn't really make it work, right? So that does make sense. The time does seem right, but that was actually a different from the question that I wanted to ask, was that I think because you're talking about the algorithms working easier on it, how reproducible are they? So I guess you probably only have one hand now, but like if I train something on one hand, do you think it'll work on the other hand? Or is that like something you're still working on? Or do you think you need to like do a sweep of 10 hands and then that'll be good enough for your hand foundation model? Or I don't know. What are your thoughts?
Yeah. I think we'll have to do some truth seeking there, because even other than the model side, like the tolerance on the hardware and the repeatability of the hardware is going to play a role here, right? So like the short answer is I don't know. But here's a few
fair enough.
but here's a few things. I guess it's some of my hypothesis, right, from studying like high dimensional dynamical systems, is that even if you cannot predict their trajectory, but they have the similar attractors. The notion of attractor is only related to complex, chaotic dynamical systems. And when the attractor is similar, is like when you train a machine learning model, there's some foundation that you can bank on. So that gives me the hope that even if, say, we have a very bad tolerance on the hardware, there will be some transferability, right? And that we'll find out around the end of the year.
Yeah, makes sense.
Yeah.
I'm sure there's things you can do, right? Like you were talking about how you could drop out some part of the tendons. So I'm sure one hand could act as like many hands, or I'm sure there's stuff that could make it work, right? It'll be exciting to see what happens at the end of the year.
Yeah. And also like we're building versions that we hope to collaborate with more people as well. I call this a paradigm shift, but I don't want to just randomly pick the phrase paradigm shift. I actually looked up some of the definitions. So there's a book called I believe it's called The Nature of Scientific Revolution. And it defines a paradigm shift as something that's very new, very contrarian to the previous approaches, but yet you have a group of follower. I guess I'm getting a group of follower on my X account, first of all. But the second part, I think is even more important, is that it opens up many new questions for people to work on, right? And I think some of the questions that you posted, Chris, about the repeatability, and also, like I said, the attractor of these things, I think these are very enticing questions for researchers and for people from industries.
Okay. Well, I guess looking out a little bit, what would you say in a few years' time, what would be something that Daxo Robotics will be able to do, or like the community on all this new paradigm? Let's say in 3 years' time. I don't know whether
in
it's
2
too
years.
far out.
In 2 years?
2 years. Okay.
Okay. So how about I say 15 years first, and then I talk about 2 years.
Okay, sure.
I don't think there is, hot take. I don't think there's a great robotics company right now. The robotics companies are all growing, but there's no robotics company that's like Apple, that's like Meta, that's like Tesla. I mean, of course, Tesla would call themselves a robotics company, right? It was first a car company. And I asked myself why, right? Of course, like DJI is great, but the thing is, they actually did not create much return for the investors at all, according to some of my investor friends. Okay. And I think about how to really move towards a great robotics company. And I think there are two types of robotic companies that you cannot go into. The first type is a component supplier. Components get commoditized pretty quickly. And you cannot be another integrator. You can't just, okay, buy off the shelf and then say go into a vertical and then sell your stuff, say to an automotive industry, or say to one big player in the industry. And then because you will always be overshadowed by that big player. I think the first ever great robotics company is going to be a platform, not a hardware platform, a platform for physical skills and capabilities, where you give them the hardware, very general hardware, and they can download, they can train new skills, upload it. It's almost like App Store for productivity, for entertainment, for education. So like I imagine our hands, integrated with whatever form factor in the future. Parents give it to their kid. It can start writing poem with the kids to teach them and to teach them math. It can cut your vegetables. It can peel your oranges or your mandarins for productivity. And of course, if people want to entertain themselves with a hand, they can always find different ways. So that's yeah. So like
Okay.
that's how I see a robotics company to become truly great. Right now, for us, how do we get there? I think to get to that point, there are two things that are very difficult from a technical perspective. And also, I'd love to hear your opinion about this as well. The first thing is skill acquisition. That's what the entire ecosystem is working on. Reinforcement learning, imitation learning, simulation or no simulation, or real world, reinforcement learning. People are taking different bets. All the infrastructure is being developed. Okay, skill acquisition. And the second part is cross embodiment. I don't think people talk about cross embodiment enough. I mean, humanoid robotics is basically a way to address that, right? Like cross embodiment, right? But the thing is, so we think that our approach is actually more general on a fundamental level. That now, if you can train a brain for every single finger, you can compose them anyhow. In the future, you can distribute your hand however you want. People can acquire new skills with it. So this is the true general embodiment. And we think that we're the only one who's on the right track for solving cross embodiment problem right now, right? Okay. Now, with that said, what we're gonna do for the next 2 years, I still think we have to find a first beachhead. So say a vertical, or maybe, I don't know, even a consumer product. Some of the investors have been talking about, what about consumer product, right? I mean, it's kind of scary because there's a lot of marketing and stuff like that. But our North Star would be to establish that skill acquisition pipeline ASAP with our hardware, right? And we have the first mover advantage because we have the only hardware that's like this. But the thing is, if we're able to establish that skill acquisition pipeline fast, it's going to be great. And the other question that people ask me is, so what's your tech moat, right? And, in the US, people are assuming that, hardware is going to be commoditized. So their moat will be on the intelligence. While the Chinese companies, they're assuming, wow, the intelligence will be open source like DeepSeek. So whatever hardware that they're building is going to be the moat. But in my honest opinion, I don't think there's any tech moat. I think the true moat for robotics companies in the future, it will be the operations, your distribution channel, your manufacturing costs, all of that, right? So or can you scale? So whatever we do about the technology right now should enable better distribution, should enable lowering cost as you leverage more economies of scale. That's how we should build technology. And that's why, our North Star is that skill acquisition, because that's going to make our distribution so easy in the future and make our robots so easy to use, right? So we're in the middle of market discovery, and whoever, I guess, is listening to this podcast in the future, if they have good use cases, I love to chat. And also, if you want to join our team, if you're, I'm also happy to chat. Yeah.
Okay. So I really like this, but so do you think that you need so to learn skills, do you need to get the hand to the place where the skill's going to happen? Do you think do you see a Daxo building a full tendon-driven robot or continue to drive soft humanoid or anything like that, like a clone kind of thing, or what do you think?
Yeah, we're integrating ARM very soon.
Yeah,
we already have a view of
your own arm, not an off-the-shelf arm.
No, it's off-the-shelf arm.
Okay, yeah, makes sense.
It's off-the-shelf arm for the first version because we really prioritize our speed. And I'm not so hung up on the mobile base yet or legs, because I think with a pair of arm, you can do a lot on a stationary workbench. And I think people need these mobile bases because they realize they cannot peel an orange. That's why they have to move boxes around. But then say if our hand is truly capable of peel an orange, chopping fruits, peeling them. I keep saying fruits because I guess I came from the fruit industry. Yeah, but yeah, like all these tasks, I think they're highly valuable and you don't have to move around. But the thing is that people just didn't have the good system for solving these tasks, right? And that's why we're going to integrate ARM. That's very, very important. But for mobile basis, it's so competitive and it's so commoditized that we're not worried.
Yeah, makes sense.
Yeah. I think you're definitely onto something here. This is like, I mean, just by the look of it, it's super unique. And I think all the things that you mentioned, there are some very unique insight. Yeah, it looks to me something potentially very, very scalable. I imagine these things, once you have some volume, the cost will go down like very fast.
Yeah.
And then the more hands you get out there, the more skill sets you get to acquire, right? Like you said.
Yeah, exactly.
Cool. So I guess maybe, a final thing for the audience. I mean, you mentioned, anyone who have specific use case, but any other thing that you wanna, you wanna ask, the community to collaborate on? Are there some specific researchers that do certain kind of research that you love to collaborate on? That sort of stuff.
Yeah, so like overall, like we don't have that much of bandwidth. I didn't mention, but we only have a team of 3 engineers. Including myself. So we're a very small team, we're very lean. So we don't have the bandwidth to work with everyone, right? But but we are open to conversations with people who are doing dexterous manipulation research, especially on the machine learning side. And so if anyone's interested or have good ideas about the kind of learning that they can do on this hand, we would love to chat, right? Maybe we can have just one group of researchers from different institutions working with our system, and we can write a paper, we can publish something, or we're basically open to conversations right now. And the other thing is, this is really a fundamental philosophical shift, right? We also welcome just feedback, especially critical feedbacks, because I think that's the only way for us to see the blind spots and to further improve on this. So for example, our videos, I did not do any promotion on Chinese social media. I did not even want to have this on Chinese social media because it's so competitive there. But a lot of these accounts, they move our stuff there, and I see people are like talking shit about our system, and I feel good. So first of all, that means it will be less likely for them to to copy our stuff. And the second thing is, I'm learning a lot from like what people say, right? People can express concerns about the payload, about the precision and stuff like that, and I can check my boxes. Okay, payload check, precision check, right? So I'd love to hear just negative and like critical feedbacks from people like overall. That's how we feel our growth.
Great. Yeah.
All right. Yeah, it's been a really fascinating chat, Tom.
Yeah.
I felt that you are definitely on a very, very unique, like you say, probably a paradigm shift. I myself, looking at this hardware stuff, I actually, oftentimes people ask, like, what is the bottleneck to the ChatGPT of robotics, right?
Mm-hmm.
Most people would say it's the AI. I actually think it's 50-50. So the hardware is equally important. So when I saw what you were doing, I was like, okay, you're doing something very, very unique. And I think you have very unique insight and philosophy around these things. And I like it a lot because it has a lot of similarity to actually how biology, how nature has evolved.
Mm-hmm.
Yeah.
Yeah, right.
In a way, it's simple and yet very complex.
Yeah.
The emergent properties.
Yeah,
Right.
yeah.
Yeah, if you want that robot chat GPT, you've got to get a lot of data or whatever. And that means you need robots that you can scale, right? And that will always work and that you can build a lot of. And I really like this direction for that, right?
Yeah, yeah. And also, so like about data, right? Just, I guess we're already about to end the podcast, but just one technical thing I would love to like discuss is about data. We have people who are expressing, oh, wow, there's more degrees of freedom. That also means that it requires more data. But then we also think that because we have 5 fingers, you can bind 2 fingers together and the other 3 fingers together. Now that's a parallel jaw gripper with more friction too, right? So like when we're controlling the fingers, it's not like we control 108 motors independently. It's actually on a low dimensional manifold, and we can control how low that dimension is. It's like if we treat this as a gripper, that's just like 1 degree of freedom. if we treat this as, say, like a 3-finger hand by binding the fingers together, then it's also like lower dimensional, but maybe more than the parallel jaw gripper. But like what I'm really concerned with is, okay, do we have extra capacity? Say like some of these very impressive like demos from say like Daxo Robotics, they're able to reach 60% of human speed and with incredible consistency. But I ask myself, okay, why can't you push beyond 60%? Is it because the parallel jaw grippers just don't have the extra capacity? And if at some point, say, when we train it for a parallel jaw gripper, we can do it. We can release some of the control, and then perhaps we'll be able to explore and leverage more of that capacity to increase the speed. That's another thing that that came to my mind when I see all these like impressive demos, and it's like think about, okay, why can't they go more? Where's the extra capacity going to be from? Is it going to be from the intelligence, or has the intelligence capped? So it's a big open question, but I think about it all the time.
Yeah. Definitely.
Yeah. I mean, my own gut feel is it's 50-50. Like, depending on, I guess, on the specific task. But a lot of times it's the hardware's not good enough. Even if it's in a demo, it looks impressive, but maybe the next attempt they do, the actuator overheat, and that's it.
Yeah.
The whole robot, you need to set it aside for half an hour to rest. All these things. But I mean, just a shout out to the guys at Dyna. I think it's one of the rare demos where they actually do it, 24 hours continuous. So that was super impressive. So kudos to them. But I mean, to your point as well, I think, hardware, it's always defines the upper limit of what you can do physically.
Yeah. Yeah.
So I can totally imagine something like yours, if it truly works a lot better, it can unlock, maybe not just in terms of speed, but maybe just like even more dexterous things. We were just talking about origami, right? I think to full origami, it would highly likely have to be something like what you're building, Tom.
Yeah.
Hard for me to imagine a really big hand with, direct drives that have the kind of extreme dexterity that, grandmaster origami master would be able to do.
Yeah. Oh, yeah. So, yeah, absolutely. And so remember, like, this is only the beginning, right? We started working on this like late March. So it's been about 5 months now. And for the past 2 months, we're basically discovering all different sorts of skills. And around the end of the year or Q1 2026, you're going to see something completely different because we have the recipe on scaling up our performance. So maybe more videos would come out. Or maybe when it's too good, we'd love to be secret.
What will really go viral is that you just have different versions of your hands, like flipping the middle finger, like just different versions, different speed, and then do it completely the other way. I was like, oh gosh.
Yeah.
Anyway. But sorry, one last question.
Yeah.
Are we gonna start being able to buy from you these things soon? What's your plan there?
Yeah, so we have to have a lot more internal discussion about this. Do we want to sell the hand as a component, or are we going to go directly to, we probably would have versions of the hand that we give out to like researchers to do some of the skill discovery or say some of the new algorithms, discovery. But then whether we sell it or not, it's a constant debate. We should have a decision in a few weeks or in a few months. So there's a lot of stuff going on. And also, by the way, we just moved from Philadelphia to Austin, and our robot is still being shipped. And by the way, it's still on its way. So it's a lot of like moving blocks. So we all seriously think about this question, and then I'll get back to, I guess, you and the community very soon.
Okay. Yeah, super
awesome.
looking forward to that. I would love to buy a few pairs to try out.
Okay. Yeah.
Yeah. I mean,
cool.
they're not that expensive, like you say. I mean, I don't know at what price you're gonna price it, but still,
Right.
I think it's
if each one's made by hand by Tom, I think they're gonna be expensive than
the one that is
each.
handmade by Tom. Yeah, with the signature. Yeah.
Look, Sharper Hands sells for $50,000, I think. So if we can build our hand to be better than their hand, maybe we should sell for more.
Yeah. Well, I mean, you look at I look at these things in a little bit like sometimes in dollar per DOF in a way, a little bit, right. So that's how one way to price these things, I feel, right?
Yeah.
Of course, not every DOF is the same, so.
Yeah.
But yeah.
Yeah. And just like one last thing, I did talk to some manufacturers of artificial muscles. Yeah, I think this is another very, very important thing that I should like touch on before we end this, is people ask me, okay, why don't you use artificial muscles? And I talk to these like a twisted
What is artificial muscle?
Artificial muscle is basically a fiber when you apply a voltage somewhere, it should be able to contract or extend.
I see. Okay.
Okay, because that's going to be the most compact format for our robotic hand, right? And that's going to make the form factors almost like your human forearm or even less. But now the problem with that is this, right? Right now we use 108 motors, and when it's operating, it's about 20 watts. If I use artificial muscle to achieve the same payload, it's going to be about 2,000 watts.
Okay.
It's
all right. No,
yeah.
I guess.
Yeah, a lot of them are based on heating, right? Heating of a polymer or a carbon nanotube or like a memory alloy. And so when you are heating is the least efficient method of energy conversion. But then there's another way that people are exploring right now is using electrolyte, using chemical reactions. That is going to be way more efficient, almost like how we are using our ATP, to activate all the muscle functions and stuff like that. I'm very bullish on that. But the thing is still in the research phase. I do think that, say, in maybe 10 years, when that's ready, and our algorithm and our robot is already like running around, we can just use that artificial muscle to make our form factor a lot smaller. So we're looking ahead there to think about, okay, in 10 years, we'll make our technology just like have another tipping point to make things even better, 10 times better, right? So I'm very excited about artificial muscles.
It's strange to think that in like 10 or 15 years, all of our robots will be squishy.
It's all going to be Westworld, maybe 10, 15 years time. Westworld, man. Yeah.
A weird future.
It's all coming true.
Yeah.
Yeah, that's, yeah. Okay. But anyway, Tom, thank you so much for the time.
Thank you for inviting.
Really really fascinating chat. I think you have a very, very interesting take on a bunch of these things. Yeah. Thanks for making the time.
Yeah.
Looking forward to all your new videos and your announcements.
Of course. Yeah.
Cool.
And it's good to see you, Chris. We always interact, but this is the first time we actually talk.
Yeah, it's great to be face to face.
Yeah.
It's really cool stuff. Really exciting. Yeah.
Cool. Yeah. Awesome. Thank you, guys.
All right. Cool. All right. All right. Till the next time.
Bye.